This is Dr. Holt. In this video I have three masses, a 10 kilogram, a 5 kilogram, and a 4 kilogram. And what I'm going to do here, I have a 538 Newton force being applied to the 10 kilogram, and we want to determine what the acceleration is going to be of the system itself, what the forces will be on each one of these masses. Alright, if you have a problem like this, I'm going to start on the 4 kilogram first, kind of draw on free body diagrams here. I'm also going to include, which wouldn't necessarily be part of the free body diagram, but the mass times the acceleration. So we'll start out here. We'll make this is just going to be our mass times acceleration. We'll make that times 4 times A here. Now we're going to do mass times gravity here, which will give me 39.2 newtons. And this will be the force. The 5 will be on the 4. So this is the force that the 5 right here is pushing onto the 4 itself. Alright, the only other force we're going to have is the frictional force sliding here. Now you have two coefficients. You have a static and you have a kinetic. If the normal force is large enough, let's shut this off. If the normal force is large enough to prevent this object from sliding down, then we're going to use static force. If this normal force is not large enough, then we'd have to use kinetic. And we'll start this problem using the static. Now the largest static friction can only be the 39.2 newtons. Even though this force could be larger, it cannot produce a larger static force, because then what you would have would be the object would accelerate upward as a result of this force being larger, which is totally illogical. Alright, so we start there. We calculate this 39.2 newtons, and we got this is our force that the 5 is on the 4. We got mass times acceleration. Alright, so we'll leave it just like that. Now when we jump over to here, we'll immediately make this into 39.2 newtons also. Now I'm going to change these. These are called force pairs right here. I'll just change color of these real quick to red. And red. Okay? Alright. So then when we get to the 5, we do 5 times 9.8. And we get 49 newtons coming down here. Now this right here is going to be the force that the 4 is pushing onto the 5. And again, I'll color these. This one. Oops, do it again. Grab this one. Let me hit the right one, maybe. Okay, this one and this one again are force pairs. Change this back to black, this one. Okay, so we've got a force pair here and force pair here. Again, this is the force pushing on the 5, the force the 5 is pushing on the 4. There's exactly the same magnitude there, just opposite directions. Now we come here. This force right here would be the force that the 10 is pushing on the 5. We'll have our mass times acceleration coming here. Now this is going to be the frictional force here. The frictional force here is just going to be the sum of these two. That's the maximum it can be. If the object is not moving, it has to. If these two objects are not sliding down, then this frictional force has to be the sum of those. So we have 49 plus 39.2. I guess 88.2. Okay, so immediately we have 88.2. We come down here and we make this 88.2. We'll change the color of this. Again, we got another set of force pairs. Okay, so force pair here, force pair here. Now here we have the 10 times 9.8 coming down. That gives me 98 newtons there. We add those two together. Our force normal is going to be 186.2. Alright, this would be the 538. Again, we're looking at all the forces on the 10. That'd be newtons coming this way. We'll have 10A coming back this way. We'll have this force right here, which would be the force that the 5 is pushing onto the 10. And again, we got another set of force pairs here. I'll make that blue. And blue. Alright, the only thing we're missing here is going to be our frictional force here. Now this object here, the 10 kilogram, is sliding, so we use kinetic friction. We use our normal normal force times 0.3 will give me my frictional force. We'll apply that by 0.3, and we get 55.86 newtons. Alright, so we have everything drawn. We have all our force diagrams, including our mass times acceleration here. All we have to do at this point is to write up our equations. I'll scroll down here. We'll look at the first one first. We're going to basically do the summation of forces in the x direction must be equal to the mass times the acceleration in the x direction. Right, and those are vector quantities here and here. So when we do that, we will have the force that the 5 is pushing onto the 4 must equal to 4a. That's all you have in the x direction. We're not going to sum the forces in y because we know the object's not going to accelerate upward, and we know that this magnitude, the magnitude of this vector plus magnitude of this vector will cancel each other out. So that's our first equation there. We'll circle that. We go to our second equation here. We'll have minus f, and I'm going to just make this the 5 over the 4 because this one and this are in the same, just opposite directions, plus the force, the 10 is on the 5. Those are the only two forces we have, must equal to 5a. That's our second equation. We go to our third equation. We're going to have our friction, which is minus 55.86. Now we have the F of the 5 pushing onto the 10, so we'll just make it the 10 onto the 5, just so we don't get these confused. Because again, they are the same magnitude. And we have 538 going to the right. Must equal to 10a. Alright, at this point you could solve this through substitution. I'm going to set up a matrices, and what I'm going to do here is I'm set up as the the force of 5 onto the 4. We'll have the force of the 10 onto the 5. We'll have the acceleration, and we'll have our values. We take to our first one, we'll put a 1 here, we'll put a 0 here, we'll put a 4 here, and we have a 0 here. We come to this one, put a minus 1 here, we put a 1 here, we put move this to the other side. Oops, excuse me, go back to this one. I need to change that. That means minus 4. Move this to the right or left. Move this to the left, minus 5 is equal to 0. Again, be very careful about that. Do not make the mistakes I'm making. Now I'll make this negative 1 here. One here. And when you do set up these matrices, make sure you move everything to the right. So like this equation here, I'm going to rewrite everything just to play it safe. This one I'm going to do f the 5 on the 4 minus 4a is equal to 0. That'll be equation 1. I'll take this equation here, I'll move it minus f 5 on 4 plus f 10 on 5 minus 5a is equal to 0. And same way with this equation here, I'm going to take the do this one minus f of 10 onto the 5. Let's see what else we got. I guess that's all. And then we got the minus 10a. And then these two, I'm going to add these together and move them to the other side. So let me do the calculator real quick with that one. I guess these minus 482. Make that 8 a little bit better. You can't quite read that. Okay, so these are the three equations I'm going to use in the matrices. I'll scroll down here. So I'll set this up as f 5 onto the 4, f 10 onto the 5, my acceleration, and then my value here. Put this in like this, put this in like this. Come to the first equation, we put a 1 in for the 5, 4. We have no 10, 5, so we put that in. 0, we have minus 4, and we have 0 here. We come to the second equation, we put a minus 1 into here. We have a 0, oh, I'm sorry, we have a 1 there, a minus 5 here, and we have 0 here. We come to this one, we have 0, we have minus 1, we have minus 10, and we have minus 482.14. I have a 3 by 4 matrices. We'll go ahead and put everything in. I'll just set up my calculator. Alright, we got 3 in here, 4 in here. Alright, so start putting in the coefficients. I got a 1, I got a 0, I got a minus 4, I got a 0, I got a minus 1, I got a 1, I got a minus 5, I got a 0, I got a 0, a minus 1, a minus 10, and a minus 482.14. Go ahead and solve its matrices on the calculator. Again, I think this is the quickest way to do this problem. And when you do this problem now, you will find that F force of the 5 onto the 4 is equal to 101.50. The force of the 10 onto the 5 is equal to 228.38 newtons. And then your acceleration of your system is going to be 25.38 meters per second squared. Alright, so that's your answer. Now let's just go back while we're here, and I just want to prove one thing. This frictional force here, we got 39.2. We had a coefficient of friction here of 0.4 static and 0.3 kinetic. If I take the force that we have here, 101.5, if I take 101.5 and then multiply it by the coefficient of friction of static times 0.4, I get a value of 40.6 being my frictional force. The thing you have to be careful about, do not make that frictional force 40.6. That frictional force can only be the mass times the gravity going down. This object cannot accelerate upward. Okay, because remember, the normal force times mu is the largest possible force that could generate in a static frictional realm. However, you only have a force that's pushing down the other way of 39.2, so frictional force can only be 39.2. So just be careful with those. Alright, that's the solution to that problem. Hope that helped you as far as how to work a problem where you have three masses like this situation, and you have a force being applied and the system is moving to the right with an acceleration.